All right. Well, good morning, all of you. This is going to be our last of our sequence of lectures on Markov decision processes and reinforcement learning. And we're going to see some fun things today where we're going to spend some of our time watching some clips also that come out of a movie about AlphaGo, which was a huge triumph for using reinforcement learning to solve very complicated problems. And I was tempted there to say real world problems, but Finale, let's talk about this. I think you're on mute. Yeah, I mean, is Go a real world problem?
Is Go a real world problem? Well, let's see. Like it's got a very clear objective function, like all real world problems, right? We know exactly
okay, so
when we want. Yes, and we
Let's
can play it a zillion times in simulation to our heart's content. Nothing bad ever happens if we truly make a mistake. Yes.
Nothing bad if we make a mistake. Okay, so far we know the reward function. We can simulate it to our heart's content. Nothing bad happens if we make a mistake. Okay.
Right. So, and also just like, what's the cleverness that we need, right? We just need a very specific type of, we need to understand the battlefield strategy, which I don't know how you use that cleverness to like manage your schedule with all the zillion like kids need snacks and grants are due, and how do you manage your finances, and then there's a research problem that you also need to solve. And
right. Yeah. I guess we could say it's a narrow problem in the AI vernacular.
I mean, not to discount what it's done, right? This is certainly a very challenging game, and there was a while where people thought it would never be solved. I think that's kind of why it was such a big deal.
I remember when I was in graduate school, my advisor was really into trying to solve it, and he thought it would never be solved.
That's right. People were like, checkers, you can bottom out checkers. You can solve checkers till you play it. You can solve out the entire game. You can simulate for the entire game. You will win every single time. And chess, but like Go was supposed to be completely beyond anything like chess or checkers.
Yeah. One other thing, or I suppose two other things we should point to when we talk about the difference between being able to solve Go and being able to have an AI that helps us in a robust way in our lives is that the actions are well defined.
Yes.
And are small. There's a relatively small action set, it does have a very large state space cherry, but also the states are well defined.
Yeah, so we observe them, right? We see the board.
And we observe them. And that's one thing that I have not been emphasizing in this part of our course. I haven't been emphasizing these challenges around missing observations. Notice I've been assuming that we have access to the state. There are things called partially observable Markov decision processes that we're not dealing with in this course, but which are what you get to when you're not able to observe the state. And in Go, you just look at the board and you see the entire state.
That's right. In most real situations, you wouldn't have access to that. If we're trying to treat patients, we don't actually know what's going on inside their bodies. We have some measurements. And even that, we have what they tell us about their home or their environment, but we don't know all of their exposures, for example, to chemicals or stressors. And all of
I have a lot of missing information. Okay, so that's some backdrop. This is the contours of what we'll be talking about in class today. And as I said, we have some kind of interesting material to get through. We're going to start by jumping to model-based learning. We want to spend just a few minutes going briefly through model-based learning because we skipped through to talk about Q learning and SASA learning last week. So I'm going to backtrack a little bit. And then we're going to get back to Q and SASA. And then we're going to talk about other forms of reinforcement learning. And we're going to try to tie all of this into success with games like Go. So to get started, let's talk about model-based learning. Just as a note, this is going to be brief. When we're doing model-based, we're acting, say, for M steps. That gives us data. We're learning a model, and then we're planning. And then we're using that plan then to decide how to act. This is how to think about model-based reinforcement learning. Now, the key challenge is how to balance explore and exploit, as I mentioned last lecture. I want to just briefly give you two ideas for how to do that when you're doing model-based learning. So one idea we can call optimism under uncertainty. And to describe this to you, let me introduce just a little bit of notation. Let's write NSA for the number of times that we have visited state S and action A. So I'm going to use the word visit for in state S and take action A. We visit the state action pair. And then the idea with optimism under uncertainty is it's a trick that we adopt while we're learning, where what we're going to say is that if NSA is small, say smaller than some threshold that you define, then we'll assume that the next state has high reward. So kind of as we'll assume, if you want to draw a little picture, it's kind of like we'll land in a state that will provide the maximum reward, R max, and we'll stay in that state. So we can think about this as an optimistic model. You're learning a model from data, but if you notice that you have very little data for a given state action, then you'll assume optimism. You'll assume if you take that action in that state, you'll get into this nirvana where you keep getting Rmax all the time. And then if you use that optimistic model for planning, then you plan with the optimistic model. And hopefully what you can see is that if I plan with that optimistic model, it's going to lead me to choose to explore where I don't know very much. So it's going to lead to this idea of we'll either do well or learn new things. So very simple idea, optimistic about things that you don't yet know, and that will lead you to purposefully explore as a planning-based or a model-based reinforcement learner. I'm not getting into details on these. I just want to give you kind of the high-level ideas of how two different approaches work. Another high-level idea that I want to give you is what we'll call posterior sampling. This is also sometimes called Thompson sampling. And if you've heard of multi-arm bandits problems, it's a very, very successful approach for solving multi-arm bandits problems. The idea I just want to convey to you is that you maintain a posterior, say a Dirichlet. Remember, Dirichlet's are nice because they're conjugates to multinomial distributions. We've seen Dirichlet's before. On the transition so for each state action, maintain a posterior over what that distribution over next state looks like. And then sample that posterior to get a model. So you have what your transition function might look like. You sample from that. That gives you a particular transition function. Let's call that a model, and then plan with it. And just to draw a picture of how to think about this. If you have good knowledge, let's say I'm plotting here the probability of a win. Let's say you're just trying to win or lose. Maybe think about Go if you like. And suppose you have two different actions, action 1 and action 2. And you're trying to learn the probability of transitioning to a state where you'll win the game. And your distributions might look like that, or your distributions might look more flat like this. And the idea here is that we would sample from this posterior. So maybe here the sample would be these two samples, but over here, you could imagine how you might sample such that the samples are flipped. And so here you would play A2, and here you would sometimes play A1. Because sometimes when you take your samples, you'll flip the order of them. So notice that if you have uncertainty about the model, then you may sometimes choose to explore, but as you become more certain, you'll be essentially more exploiting the knowledge that you have. So these are two quick ideas for model-based learning. I don't really want you to know more than this about these ideas, but if you wanted to explore this more, you could. So I'll just point out that we put optimism here. That was the first idea. And then the second idea was we sampled here. So those are the two ideas I described to help you to balance, explore, and exploit. And we talked last class about the trade-offs involving model-based approaches versus model-free approaches. Okay, any questions about that before I continue? Because what I'm going to talk about next is I'm going to start getting back into model-free reinforcement learning. And I see Charu's asking, is this kind of like epsilon greedy analogies? Yes, you can think about it that way. So epsilon greedy is another way to balance explore, exploit. All right, so now let's get back into model-free reinforcement learning, where, remember, the picture we have is I have an agent that's learning Q values. I have my world. The agent is acting in the world. The world is delivering experience. And we've got two kinds of things that we need to be thinking about. One is the behavior of the agent, which is how is it choosing to act. And here you could think about greedy, or you could think about epsilon greedy, or other ideas. And then the other thing that's going on is you have the learning behavior of the agent. And here you could be thinking about Sarsa. You could be thinking about Q-learning, etc. So somehow these two things are separate. You can choose your behavior, you can choose your learning approach, but you have to also understand a little bit about how they go together with each other. And I want to talk around that a little bit today. So just to recall, we have this idea of an optimal Q value, which is the value from taking an action A and state S, plus the expected discounted value you get for continuing optimally. So think about these as the Bellman equations that define Q star. And remember that if we have the Q star values, then we know how to act by choosing the action that maximizes the Q star. And then we talked about two different ways to learn. One was to use SARSA. I'm going to write now the learning rate as a function of the state and action, because I want to just be a little bit more precise about some of the theoretical things that you can say about SARSA and Q learning. So I'm just making this a little bit more precise, which will allow the learning rate to depend on the state action. So that's a function now of the state and the action. Okay, so that's our SARSA update. This is on policy. What does that mean? What that means is that it learns Q values that correspond with the behavior. That's SARSA. And the other algorithm we talked about is Q learning. And Q learning has almost the same learning rule, except it looks a little bit more like the Bellman equations. Because it has this max here. Okay, that's our Q learning update. This is an off-policy method. And what that means is that it is trying to learn Q values that correspond to the Bellman equations, i.e. Q star. So crucial thing to notice is that the thing you learn with SARSA depends on the way you behave. You hope that Q learning will learn optimal Q stars however you behave. That's the on policy versus off policy idea. Any questions? Okay. So I want to state a theorem. I'm not going to prove a theorem. It's a little bit hard to prove, but I want to state a theorem. And to state the theorem, I'm just going to require that the learning rate for a given state action is 0 unless the state action is visited at t. So the learning rate is 0 for all state actions that you haven't just visited, which I think is how you've been thinking about things anyway, because we're only making the update for the state action that we visit. So here's a theorem. Qlearn converges to Q star as t goes to infinity. the number of steps you're acting in the world, as long as 1, this is true, the sum of the learning rates, remember they have to be 0 for state actions that you're not visiting, should be infinite for all state actions. And 2, the sum of the square of the learning rates should be less than infinity. I'll interpret those for you in a second. And I also want to say that this is the second part of my theorem statement, that for saucer to converge to Q star, you also need 3, that the behavior is greedy in the limit. What does that mean? That means that it eventually follows the Q values. So if you're using epsilon greedy, epsilon has to eventually go to 0. We don't need that condition for Q learning. We only need that condition for saucer because only saucer is on policy. So let me make some remarks and interpret the theorem for you. 1, to get this alpha t summing out to infinity property, we need to visit each state action infinitely often. Because the learning rates, think about them as being bounded by 1. So if the sum sums up to infinity, you'd better visit each of the state actions infinitely often. And this is the role of something like epsilon greedy. To make sure that you get enough experience of different states and actions. 2, for this thing to be less than infinity, and I'm not writing down the S's and the A's here, just this is just shorthand, then you need to reduce the learning rate. And one typical way that's done is to set the learning rate to be 1 over the number of times that state action has been visited so far. So you decay the learning rate as you accumulate more experience in visiting a particular state action. And then 3, what is this greedy in the limit? Well, a typical approach would be to set epsilon on the state. This is the epsilon in epsilon greedy to be something like the number of times that you have visited that state. So again, I'm not proving this theorem for you, but I'm stating it because I think it gives you a little bit of scaffolding to think about what these methods are. I'm always reluctant to state theorems without suggesting parts of the proofs, but I'm not going to do that other than to say there are Bellman equation contraction style ideas happening behind the scenes we're not going to get into. You may also be thinking, well, this theorem seems like somewhat weak because it's talking about having to visit things infinitely often. And I agree with you, but it is a theorem statement. And it doesn't mean that these algorithms are only useful if you are to visit things infinitely often, but it gives us at least a formal thing that we can say about them. Any questions about the statements of the theorem? Okay. So what I want to do now is I want to show you all a video. Melissa asks if we're not visiting a state in a given time. Yes, then alpha t is 0. Exactly. That's what I said at the top here. That's right. I'm going to show you a video. I wanted to the benefits of SAS over Q-learning. SAS is a simpler algorithm, I think is the best thing to say there. Now, one of the interesting things that happened with reinforcement learning in recent years is that we found that by combining Q-learning with neural networks, we're able to learn to play games of Atari. So here are, Atari was this video console in the 1980s that I used to play with my friends. My friend had one of these, so I would go over to his house and we'd play all these games, and they were fun at the time, I guarantee it. So here are just some examples of those games. And DeepMind, which was founded by Demis Hassibis, who is an AI neuroscientist in the UK, decided that using Atari games would be a good experiment to see if we can train through a single AI architecture the capability to play across multiple different games. And I want to show you a video of Demis Hassibis talking about that success. This is when he visited Oxford University. He's going to be walking around with Mike Waldridge, who's an AI researcher at Oxford, and he's going to be giving a talk in the Sheldonian Theatre. Random note on that is that I got my degree in that theatre when I was at Oxford.
When I was a kid, I loved playing games. I started off with board games like chess, and then I bought my first computer when I was 8 with winnings from a chess tournament. Ever since then, I felt that computers were this sort of magical device that could extend the power of your mind.
Virtual environments in games. We think they're the perfect platform for developing and testing AI algorithms. Games are very convenient in that a lot of them have scores, so it's very easy to measure incremental progress. So I'm going to show you a few videos of the agent system, the AI. So let's start off with Breakout. So here you control the bat and ball, and you're trying to break through this rainbow-colored wall. The agent system has to learn everything for itself, just from the raw pixels. It doesn't know what it's controlling. It doesn't even know what the object of the game is. Now, at the beginning, after 100 games, you can see the agent is not very good. It's missing the ball most of the time, but it's starting to get the hang of the idea that the bat should go towards the ball. Now, after 300 games, it's about as good as any human can play this, and pretty much gets the ball back every time. We thought, well, that's pretty cool, but we left the system playing for another 200 games. And it did this amazing thing. It found the optimal strategy was to dig a tunnel around the side and put the ball around the back of the wall. The researchers working on this, amazing AI developers, but they're not so good at Breakout. And they didn't know about that strategy, so they learned something from their own system, which is pretty funny and quite instructive, I think, about the potential for general AI. So for us, what's the next step now? Go is the most complex game pretty much ever devised by man. Beating a professional player at Go is a long-standing grand challenge of AI research.
That is something we're going to get back to, but before we get back to that, I want to tell you how the reinforcement learning for solving Atari worked. So here's how the reinforcement learning for solving Atari worked. So these are called deep Q networks. And first of all, what is the state representation that is used for Atari games? It is a 84 by 84 pixel map and by 4 in this direction. So this is a raw input, because we don't do any processing other than downsampling the screen size and grayscaling it. Gray-scaled pixel map. So it's 84 by 84 pixels. And then the 4 dimensions are the 4 most recent frames. And that's trying to make the state representation more Markovian, so that by looking at the 4 most recent frames, you can understand the future trajectory and the future dynamics without knowing anything more about the past. That's why you take 4 frames rather than 1 frame. So you can see which way things are moving, for example. Now, there were 3 big ideas in DQM. The first idea 1, is to notice that the tabular representation fails. Couldn't possibly represent all of those states using a tabular representation of the Q value. And so what you do instead is you parameterize the Q value with parameters W, and you use a differentiable deep network, in particular a convolutional neural network. That's the first idea. Second idea is that now you do gradient descent on the temporal difference error. This is, I didn't emphasize it, but this is exactly what we've been using here. This is the TD error. So the difference between this and this Q, we call the TD error. I mentioned that last lecture. So we're going to do gradient descent on the TD error. What does that mean? Well, here's what that means. And the thing I also like about this is you're seeing the first part of the course now come together with the second part of the course. Because you're seeing gradients coming back now, and you're seeing parameters and neural networks coming back. We're going to use a squared loss Okay, so this is very familiar to you, except you haven't seen me write this as a gradient with regard to a differentiable Q function before. And also I just noticed that I should write my parameters here. And this is my learning rate still. And then what I'm doing is I'm trying to use my data. Think about your data as, again, being state, action, reward, state primes. And I'm trying to use my data to minimize the squared error between my kind of estimated Q value for the next state and my current Q value. This is very familiar to things that we've seen so far. And what we can do now is we can take the gradient of all of this. And what we would get is we would get plus alpha t. We just use the chain rule. And I'm writing W alt here just to recognize that I'm not going to take the derivative of that Q function. I'm going to use the current W parameters, just going to hold those fixed there. I'm just going to take the derivative with regard to this term. And then using the chain rule, I had that all the way to the right. I just emphasize this is what DMind talks about as a frozen network. You're going to keep that fixed, and you're going to take the derivative with regard to this Q function here. That's the second idea. And then idea 3 is experience replay. So you're going to put R S prime into a replay buffer. Just memory, you're going to store things you've seen recently and do mini batch gradient descent. So the idea here is that you reuse experience. So these are the 3 ideas, and if you read the paper is pretty accessible. I think you are able to read the paper based on the things you know in course so far. And really, we haven't done anything here much more than bringing neural networks together with Q values and Q learning in a natural way. And I see there's a question about the derivative here. So the derivative is with regard to the Q function. We need to take the gradient. So think about taking the partial derivative of the Q values with regard to each of the parameters in your neural network. That's the gradient that we're taking here. Are there any other questions? Here, the way I've written it, it looks like a single stochastic gradient descent step where you just use your latest evidence, SA, R, and S prime, to do one update. But here the idea is that you would pick multiple pieces of evidence like that, and you would do one gradient step on the average of what you get from all of that data. Any other questions? Oliver, Al's asking, is the last Q on the vector W? Yes, this is the current W because I just used the chain rule here to take my derivative. To the right of that, yeah, this is the current W. You're taking the gradient with regard to the current W. Okay. Is the input to the network the Q values? No. The network is taking state. The network is taking state, and it is generating a Q value. Think about there being 18 actions in Atari. So it's generating 18 Q values at the output of the network. The network is literally a function approximation to what you've been thinking about so far as tabular Q functions. Other questions? Okay. And the W are the parameters in the neural network. Other questions? Okay. Now, and why do we need a neural network? Because there are probably more atoms in the universe than there are numbers of states you can write down. If you take 2 to the, what is this? This is like kind of number of states is 2 to the 84 times 84 times 4. That's pretty big. So you cannot use a tabular representation. Okay. Now, we want to try to move towards using reinforcement learning for solving the game of Go. I'm going to keep showing you parts of the movie AlphaGo, which is a 2018 movie. This part of the movie is going to describe the game of Go.
Game of Go with Demis more than 20 years ago. And so this has been a really long journey. The game of Go is the holy grail of artificial intelligence. For many years, people have looked at this game and they've thought, wow, this is just too hard. Everything we've ever tried in AI, it just falls over when you try the game of Go. And so that's why it feels like a real litmus test of progress. If we can crack Go, we know we've done something special.
So with Fan Hurry, we started talking around what the real purpose of the visit was. It wasn't just a Go project we wanted him to help with, that actually we wanted to play him, and we had a very strong program.
Oh, it's okay, just the program is so easy. So it will be easy to play.
A lot of people have thought that it was decades away. Some people thought it would be never, because
So by the way, that was Fan Hui, who was the European Go champion.
they felt that to succeed at Go, you needed human intuition.
Go is the world's oldest continuously played board game. And in some sense, it is one of the simplest and also most abstract.
There's only one type of piece, there's only one type of move, you just place that piece on the board. And then your goal is to create a linked group of your stones that surrounds some empty territory. And when you surround enemy stones, you capture them and remove them from the board. You earn points by surrounding territory, and at the end of the game, the person with the most territory wins. It seems really simple, but then you sit down to play and you realize right away, it's like, well, I technically know what I'm allowed to do, but I have no clue what I should do.
Go is incredibly challenging for computers to tackle because compared to, say, chess, the number of possible moves in a position is much larger. In chess, it's about 20. In Go, it's about 200. And the number of possible configurations of the board is more than the number of atoms in the universe. So even if you took all the computers in the world and ran them for 1 million years, that wouldn't be enough compute power to calculate all the possible variations. If you ask a great Go player why they played a particular move, sometimes they'll just tell you it felt right. So we have to come up with some kind of...
If you look very closely here, you can see Q functions.
clever algorithm to mimic what people do with their intuition.
Okay, so that's the challenge. Now, how do we go about using reinforcement learning to solve the game of Go? First thing I need to tell you about is the last method of model-free reinforcement learning that I want you to know, which is policy learning. The idea in policy learning is that we're going to adopt a differentiable policy for parameters theta. So notice I'm writing, now I'm allowing this to be a distribution. For a long time, we've just been talking about policies that return a single action. Now this is giving the probability on each action in a given state. And we're going to try to learn this policy directly. No more Q values, just learn the policy directly. The reason this might be interesting is that a policy might be simpler than a Q function. You can kind of imagine that the value function, Q function, is complex and in ways that don't matter. And the actual policy is like, go right all the time. It's not going to work for Go, but you get my point. So that's one reason we might be interested in this. And a second reason we might be interested in this is we can handle continuous actions. Not relevant for Go, but you can imagine that might be relevant for lots of real-world settings. It's harder to handle that with Q-learning because you have that max over A. Can be done, but it's harder. And the third thing is maybe we can introduce expert knowledge more easily. You can imagine that maybe experts are more able to teach you through describing how to do something than by somehow directly describing a Q function. Okay, so the question is how to train. So I've kind of given you this idea that we're going to have this differentiable policy, but how can we learn a good policy? And the high level idea is going to be that we're going to do, we'll be doing gradient ascent on a measure of the performance. So gradient ascent, trying to improve the performance. I'm just writing J theta here as shorthand for the performance of a policy parameterized by theta. And you can think about this a little bit like a value function. It's a little bit like a value function. So our data, let me try to make this precise for you, will be histories where a given history is a sequence of experience in the world. That's a given history H. I will one shorthand RH for the sum of the rewards on that history. And then I'm going to define my performance J of theta to be the expected reward over the histories that are generated by the policy. So think about a distribution over histories that accords to the rules of the policy and of course the stochastic environment as well. That's my objective. Last thing I want to define for you is I want to define the likelihood, which I'm going to write as mu theta h. This is the likelihood of history h when you're following policy pi theta. And this, because of the nice structure, the nice factored MDP model, is the product over the actions as picked by the policy and the transitions as picked by the world. So there's a factored representation for the probability, I have to call it likelihood, on history H. And that's coming from the structure of the MDP like we've seen in this course. Now, crucial thing I need to explain to you is how can I calculate this? And I'm gonna do it in a few steps. First of all, we'll just write in the definition of our performance metric, and then we'll introduce the likelihood measure. And then we'll just rearrange things. We'll notice that the reward doesn't depend on the parameters. And so I can push my gradient operator into the integral. And I'm writing an integral here because I'm thinking about there being a continuum over histories. So I'm writing it in integral form rather than in a summation form. And Oliver's asking difference between policy and Q-learning, and somehow these are building models. Well, think about these as being model-free. We'll say that a model is something that tells you what transitions you'll see in the world. Neither of these approaches, neither Q-learning nor what I'm now calling policy learning, will tell you what next state you should expect to see when you take an action. So in that sense, these are model-free approaches, not model-based approaches. And this will be a different way to learn directly how to behave, where we're not going to learn Q functions, we're just going to learn the policy directly. Now, the challenge is that this thing here seems to depend on the transition model. Because after all, I used the transition model when I wrote down my likelihood. But I don't want to have to learn my transition model. I want this to be model-free. Now, the way that we can get around this is that there's a really neat identity, which is one of these kind of beautiful happenstances of mathematics, which is that we can write I didn't change anything there. I just multiplied and divided. And now that is that by the chain rule. Yeah, this is just this. It's the gradient of the natural log of mu. So let's put that in a box. And let's get back to my derivation. So I got to this step, and now I'm going to substitute this expression for this expression. And I'm going to expand the log of my likelihood. And when I do that, my products become sums. So I'm going to get the sum over t of the log of what my policy is doing, plus the sum over t of the log of what my transition is doing. Now, the crucial observation is that this doesn't depend on theta. There's no theta there. And so there's no gradient. There's no gradient of this term. So the p's are going to drop out. And this is just equal to, now I'm just going to kind of rewrite this as an expectation. And we're going to push the gradient inside the first of my summations. I don't need my second summation because it has no gradient. And now, finally, I can write this in an even simpler form. Which is that. And we can take the gradient of this. This is nothing more than a reward that we observe multiplied by the gradient of the log of our policy. Remember, our policy is represented as a differentiable neural network. And I got rid of the mu because I rewrote this integral thing as an expectation. Remember, when I integrate out and I multiply by this likelihood, I'm actually taking the expectation with regard to everything else. The reason I wanted to derive this for you is that you will often see this expression. Like if you do any Googling around for policy learning and reinforcement learning, you'll often see this expression and it might seem to be mysterious. And now hopefully you see that it's not mysterious. So this is the idea of policy learning. We represent our policy in a differentiable way. We act according to our current policy. We collect more histories. We take a gradient step. We improve our policy, et cetera, et cetera. And let me just remark that this is on policy. You're kind of collecting data according to how you're behaving and updating your model using the history. And intuitively, you're just putting more probability on actions that bring you reward. That's what's happening here. And how do we compute the expectation? Yes, so we're going to do a gradient step on this. So we're just going to view one history as giving us an observation that lets us do a gradient step. Just as we did earlier in the course when we had expectations over the true distribution, we let the data represent the distribution for us. So you take a history, you do a gradient step. Take another history, do another gradient step. So we can do, the point is that I can now do SGD with that math. Okay. Now, so by the way, that derivation, don't worry about that for your midterm. That's out of scope for the midterm, but I wanted to show you the derivation. Now, the question is, how does something like that lead to the following madness? And I'll get back to your technical questions in a second.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
They said all is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge. The full world is watching. Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think something went wrong. Yeah, it's made a mistake. He's got to pronounce it a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Okay. Yeah, this is getting exciting. So I saw maybe there was still a little confusion, so I did just want to write up the SGD step. So this is the SGD step. I give you a history, and you just do this math, and this is your SGD step. And I think somebody asked, how did we work around the P's? That was because we were able to use this kind of identity. We have this log around this muse, and then the P's, there was no gradient of the P's. So magic, math magic. All right, now, how does AlphaGo work? How does AlphaGo work? There are going to be 3 ideas in AlphaGo. First of all, let me tell you about the state. Now I've got a 19 by 19 board. That's the size of the Go board. And I've got 48 different features hand-engineered per board position. So 48 handcrafted per position features. That's my state representation, including like whether there's a piece in that position, including something about the recent history, because there are rules in Go where you cannot repeat yourself. We're not going to get into the details of these hand-engineered features. This is the state. And then there are, when we think about learning, there is some supervised learning, and there is some reinforcement learning. And here's what the supervised learning does. It's going to generate 2 policies. One I'll call PySL for supervised learning. One I'll call PyFast for a policy that you can use very quickly with little compute time. For PySL, we're going to train a deep network to predict expert moves. So this is supervised learning. What does my network look like? State going to 19 by 19 plus 1 output units, like the positions on the board, plus 1 for pass. This is going to predict a distribution over actions. So there's a softmax layer on the output of the neural network of dimension 19 by 19 plus 1, giving you a distribution over actions that you predict the expert will play in the current state. This network has 13 convolutional layers and is trained with log likelihood loss. It's trained for 3 weeks on 50 GPUs with 30 million positions, which come from records of online Go games. That's PySL. The other thing is PyFast. Here we just train a linear softmax model with log likelihood loss and hand-coded features. Yeah, it's trying to predict what the expert would do. So that's supervised learning, and then we also use reinforcement learning. Reinforcement learning is going to use policy learning to give us a policy, pi theta, and it's also going to learn a value function, v theta. That's the product of reinforcement learning. So pi theta, we're going to use the same neural network architecture as was used for supervised learning. Same architecture. We're actually going to initialize the network to the policy from supervised learning. We're going to define a reward +1 for a win, -1 for a loss, 0 for a draw. And we're going to play 1 million games in self-play versus earlier versions. There's kind of curriculum learning flavor to this. Keep trying to bootstrap over things you've been able to do so far and learn to play better. And we're going to do policy gradients, just like what I just showed you. So this was trained for 1 day on 50 GPUs and with 1 million self-play games. And then there's this v theta, which is the MDP value function corresponding to policy pi theta. So v theta uses the same architecture. But this time it just outputs, it has a different output layer, which just outputs a number between 0 and 1, which we think about as the probability of win. So it has a logistic function on the output layer. This we train by supervised learning, where the target of supervision is win or loss coming from Monte Carlo evaluation of pi theta. What does that mean? You put yourself in a particular board position and you sample from pi theta and you see if you win or lose. That gives you a training example for the supervised learning problem. This trained for 1 week on 50 GPUs with 30 million positions. Okay. That's learning. That's how AlphaGo learns. But how does AlphaGo play? Like, how are we going to use these 4 things? How does AlphaGo play? Notice that you can basically follow all of this from this course, I hope. How does AlphaGo play? It uses guided Monte Carlo tree search. And just a note, this is very costly. This needs 48 CPUs, 8 GPUs, and 40 compute threads. Okay, a massive amount of computation here. What does it do? This is your current state. You will consider different actions that look promising from that state. And you're going to build this kind of look-ahead tree forward from your current board state. And you're going to consider different promising actions and keep kind of building out this tree forward, getting to future board states. This keeps happening until you get to what we'll call a leaf of this look-ahead tree, this is a leaf, but it may not be the end of the game. And then you do this fast rollout using PyFast. So that's one of the things I told you about that we got during learning to get to a win or loss of the game. With that information, you will calculate the value function for the leaf as the average of the value function learned by reinforcement learning and the information you got from your rollout forward to the end of the game. So I've just used this piece of information from training. The other thing that's happening is that when I build out my tree, I'm doing guided exploration. Like, how did I pick those actions? Well, I picked those actions using my supervised learned policy. And increasingly, as I keep doing my tree search, Q values that we back up from leaves. So I don't have the time to get into the details of how that backup works, but it's basically taking maxes and pushing values back up the tree. And the thing I want to emphasize is that initially I take the supervised learning as my prior to guide the expansion of the tree. I should say guided expansion. And then over time, the Q values take over, which come from this. And the thing I just want to note before we go back and watch some more video before we wrap up class this morning is that we didn't use pi theta. And they found that using pi SL for guiding expansion was more useful. But notice that we are using RL in a very serious way through these V values, and these eventually take over. Like these V values eventually flow into these Q values. Okay. I realize it's a little bit fast, but I just told you pretty much everything about the way AlphaGo works. So now let's get back to the videos. By the way, if you're wondering, there are no comprehension checks today. I just want to show you about another 5 minutes of videos and then we'll break. I know we're at 11:44, so I'm hoping you can stick around. So first of all, what happens next is this magical move 37.
Lisedal go to smoke, and AlphaGo just play. It don't think about the opponent will be there or not. So Ajab sees AlphaGo plays the move 37, and Ajab puts the stone in the board.
와 정말 생각지도 못한.
Value.
That's a very surprising move.
I thought it was a mistake.
When I see this move, for me it's just the big shock. What? Normally human will never play this one because it's bad. It's just bad. We don't know why. It's bad.
But it's a little bit high.
Yeah.
It's fifth line. Normally you don't make a shoulder hit on the fifth line.
So coming on top of a fourth line stone is really unusual.
Yeah, that's an exciting move. I think we've seen an original move here. That's the kind of move that you play Go for.
Hey.
Interesting stuff.
This fifth line shoulder hit is
I wasn't expecting that. I don't really know if it's a good or bad move at this point.
The professional commentators almost unanimously said that not a single human player would have chosen move 37. So I actually had to poke around in AlphaGo to see what AlphaGo thought. And AlphaGo actually agreed with that assessment. AlphaGo said there was a 1 in 10,000 probability that move 37 would have been played by a human player. So it knew that this was an extremely unlikely move. It went beyond its human guide, and it came up with something new and creative and different.
I am very much watching the game through the.
Okay, so now Lisadol comes back and looks at the move.
I want to see Lisadol when he sees this move.
He's back, Leah's back.
알파고는 실은 뭐 확률적 계산을 하고 그냥 이기기 위한 그런 머신에 불과하다고 생각을 했었는데 그 수를 보는 순간 아니구나. 충분히 알파고도 창의적이다. 정말 아름답고 바둑의 그런 아름다움을 잘 표현한 수고 굉장히 창의적인 수였다.
Normally he think about 1-2 minutes, no more. But this time he think more than 12 minutes. The more I see this move, I feel something changed. Maybe for human we think it's bad, but for AlphaGo, why not?
Go is like geopolitics.
Okay, so a few more clips. Hopefully you can stick with me. Now the tragedy.
Because then White, he resigned. It looks like Lisadol has just resigned.
So this is him resigning that same game.
Is he okay? I brought his friend because yesterday I noticed that he really wanted to analyze the game.
There was this heavy sadness over that whole floor. You could feel it during the game. I felt it during the game. And I'm leaving the commentary room to go to the press conference, and I was stopped by someone, another technology reporter. And at first, all he wanted to talk about was the technology and how great this was. But then even he kind of slipped into this moment of melancholy where he was upset as well.
놀란 거 자체로 충분히 놀랐고요. 이제 뭐 할 말이 없을 정도가 아닌가 싶습니다.
Now, he did win one game. Here's the triumph when he wins one of the games.
Like my win.
내가 생각하는 게 좀 싫어가지고 그냥 일정 진짜 일정에 막 이런 데 끼우는 거만 생각 못 하다가 한판은 이겼네. 정말 이 정도일 거라고는 정말 생각도 못했어. 정말 믿을 수가 없었어. 믿을 수가 없어서 이거는 진짜. 예, 감사합니다. 한 판을 이겼는데 이렇게 축하를 받아본 건 또 처음인 것 같습니다.
Okay, I just wanted to show you the final game and then about 30 seconds of reflection. So in total, 1.5 minutes left, I think.
돌을 포기할 것 같이 지금
돌통을 한번
돌통으로
만졌죠.
지금 만지고 있거든요.
Oh, except for the.
Is that what?
That's kind of a different depending.
Så nu kan
program sometimes too.
Det blir då ett
I would like
다시
to
좀 relax.
sort of weed that out.
포기할 것 같습니다. 여기까지입니다. 여기까지입니다. 여러분.
네.
여기까지입니다. 예.
But as the program is
Okay, and then just a little bit of reflection from Lisa Dahl.
This is a unique experience. Nobody can have this experience. Play with AlphaGo 5 game look like this. So I hope Lisidor can find something in this 5 game, maybe some change in his game. I see today he fight. It's very good. Big master, real big master.
이번 경험을 통해서 조금 더 성숙했다고 생각하기 때문에 그걸 정리 잘해서 앞으로 또 발전할 수 있도록 하겠습니다. 정말 내 바둑 두는 이유를 찾았다라는 느낌, 사람들이 이렇게 해줬을 때 그런 느낌? 정말 더 나아가자면 정말 바둑 잘했구나 그런 생각이 들 정도로 정말 저한테는 그 순간도 잊지 못할 것 같은 정말 그런 경험이었습니다.
And that's the thing that I like about this whole story. It's just like the human side. I think you really feel what is going to increasingly keep happening as AI does things that people don't think it can do. And Go, an example of that type of landmark in the field. So thank you for letting me share that with you. Want to walk you through to see technically how things work and also experience it.